Hello students, today in our session 7, in this lesson magnetism and magnetic effects of electric current, today we are going to see the important topics: BIOTSAVART law, the definition and explanation in this BIOTSAVART law, then similarities and differences between Coulomb and BIOTSAVART law. Next question is magnetic field due to long straight conductor which carrying the current. Magnetic field produced along the axis of the current carrying circular coil. Last one, current loop as a magnetic dipole. Let's move to the lesson now. BIOTSAVART law. In 1819, Jean-Baptiste BIOT and Felix Savart did a quantitative experiment on the force experienced by a magnet which is kept near current carrying wire, like the experiments made by the Oersted. They attained a mathematical expression that gives the magnetic field at some point in space, that is, the current that produces the magnetic field. This is true for any shape of the conductor. Using this, they defined and they explained the law, which is a BIOTSAVART law. BIOTSAVART experimentally observed that the magnitude of magnetic field dB vector at a point P at a distance r from the small elemental length taken on a conductor in the and the current varies with respect to, which is directly proportional to the strength of the current I, which is directly proportional to the strength of the current I, and which is directly proportional to the magnitude of the length element, this. Then it is directly proportional to the sine of the angle, it is theta, between DL and R. This is the angle between the DL and R. Here you can see the angle produced. Then it is also inversely as the square of the distance between the point P and the length element DL. Now, according to the law, there is an expression. It shows the magnetic field dB is directly proportional to the current, the strength of the current, which is I, and it is directly proportional to the magnitude of the element length DL. Then it is directly proportional to the sine of the angle between DL and R. Then it is inversely proportional to the square of the distance between the point P and the length element DL. And from the first equation, which is proportional, that means dB is proportional to IDL by R square sin theta. If you use a K constant, then you can equate the equation dB is equal to K into IDL by R square into sin theta. Here K is referred to mu naught by 4 pi, the SI unit, and the K is equal to 1 in CGS units. And in vector notation, dB vector is equal to mu naught by 4 pi. That means we substitute the value of K here. Mu naught by 4 pi is substituted by the value of K. IDL vector into R cap divided by R square. This is due to the vector notation. If you take integral on both sides, we get integral of dB is equal to B vector, and mu naught I by 4 pi, it's apart from the integral, so we take out of the integral, then dl by r cap into r square. If you integral that, the vector dB is perpendicular to both IDL, pointing the direction of current flow, and the vector r cap directed from dl toward the point P. Now the equation 4 is used to compute the magnetic field only due to a small length dl on the conductor. Therefore, in these cases, first one, if the point P lies on the conductor, then theta is equal to 0 degree, because therefore the dB is 0, sin 0 is equal to 0, so the derivative of that magnetic field is equal to 0. If the point lies perpendicular to the conductor, then it is 90 degree, sin 90 degree is equal to 1, therefore dB is equal to IDL divided by r square into n cap. Here n is the unit vector which is perpendicular to both IDL and r vector. Next one, similarities between the Coulomb's law and BIOTSAVART law. What are the similarities between? In electric and magnetic fields, these laws obey inverse square law, so they are long range fields. Second point, these Coulomb and BIOTSAVART's law obey the principle of superposition and are linear with respect to source in magnitude. E is proportional to Q and B is proportional to IDL. These are the similarities between Coulomb's law and BIOTSAVART. Now let's see what are the difference between Coulomb's law and BIOTSAVART law. Same as the similarities, let us see in electric field and magnetic field. First one, the electric field produced by a scalar source, that is an electric charge Q. In magnetic field, which is produced by a vector source, that is current element IDL. And in Coulomb's law, the electric field is directed along the position vector joining the source and the point at which the field is calculated. While in BIOTSAVART law, the magnetic field is directed perpendicular to the position vector R vector and the current element IDL vector. In Coulomb's law, the electric field does not depend on angle, but in the BIOTSAVART law, the magnetic field depends on the angle between the position vector R cap and the current element IDL, which we saw in the picture I showed before. Next one, a very important question. Magnetic field due to long straight conductors which carry current. Consider a long straight wire as a picture. It is Nm with current I flowing from N to M as shown. Let P be the point at a distance A from midpoint O. Let us consider an element of length dl of the wire at a distance L from the point O, and R be the vector joining the element dl with the point P. Let theta be the angle between dl vector and R cap. Then the magnetic field due to the element is dB vector, which is equal to mu naught IDL by 4 pi r square sin theta. We take this value from the BIOTSAVART law. The unit vector is perpendicular to dl and r cap. Now the direction of the field is perpendicular to the plane of the paper and going into it. The net magnetic field can be determined by integrating the above equation with proper limits. So we are going to integrate the equation dB is equal to mu naught I by 4 pi dl by r square sin theta using some proper limits. Here you can see the diagram. See, it's a long straight wire N and M, and the current is flowing in between this long straight wire. Now let's P be the point at a distance A from the midpoint O. Here you can see O is the midpoint between the M and N. Here we take a very small distance in this M and long straight wire M and N. We take a very small distance, that is dl. This is between total, and the length of the wire is is L, and the angle between the A, O and P is pi minus theta. So now tan pi minus theta is equal to A by L. Using this, tan pi minus theta is equal to A by L using a cosine law. Therefore, L is equal to minus A by tan theta. As you know, tan pi minus theta is equal to minus tan theta, right? If you put minus tan theta here, then A by L, if you take L here and minus tan theta down to A, then minus A by tan theta. Then if it is 1 by tan theta, then you can convert 1 by tan theta as A cot theta. Therefore, L is equal to minus A cot theta. In the book, they have given that R is equal to A cosecant theta. Actually, it is also derived as this tan minus theta, pi minus theta and A by L using this values. That means A, M and P. Okay, using that we have the values of R. This is the length as L, right? Then here the angle is between this A, M and P. So here we got A by secant theta, and 1 by secant theta is equal to cosecant theta. So we put R is equal to A cosecant theta. Now differentiating, dl is equal to, if you differentiate here dl, then minus A cot theta becomes A cosecant square theta into d theta. Then substitute the values in the equation 1. If you substitute, then dB is equal to mu naught I by 4 pi A cosecant square theta into d theta. That means the value of dl. Then R square is equal to A cosecant square theta from here into sin theta d theta, which is present actually in the book. Okay. Now dB is equal to mu naught I by 4 pi A cosecant square theta into d theta by A square. That means we square the A and we separate cosecant square theta to cancel the two values, cosecant square and cosecant square. Then if you cancel this cosecant square theta and cosecant square theta, then we get mu naught I by 4 pi A sin theta d theta into n cap. Students, remember, in our book they have made a small mistake. I made all these things into this video only to make you an account. When you derivate the dl, that means minus A cot theta, you get only A cosecant square theta, not this d theta. So it is wrong. D theta is wrong, and here also there is no d theta. Remember, again and again I am telling the corrections in the book. A cosecant square theta into not d theta. There is no d theta. So we can cancel only the cosecant square theta and this cosecant square theta. No other d theta left behind. That's why we get mu naught I by 4 pi a into sin theta d theta n cap. Here the sin theta d theta n cap is given from here. Right? Next. This is the magnetic field at a point P due to the current in small elemental length. Therefore, the net magnetic field at a point P can be obtained by integrating dB vector by varying the angle from theta is equal to pi 1 and theta is equal to pi 2. That is, B vector is equal to mu naught I by 4 pi a. We take that from away from the integral values and we take from pi 1 to pi 2 sin theta d theta n cap is equal to mu naught I by 4 pi a cos pi 1 minus cos pi 2 into n cap. As you know, pi 1 is equal to 0 and pi 2 is equal to pi. Therefore, for an infinitely long straight wire, pi 1 is equal to 0 and pi 2 is equal to pi, the magnetic field is mu naught I divided by 2 pi a. That means here we have the value mu naught I by 4 pi a and cos pi, that means cos 0 degree is equal to 1 minus of pi 2 is equal to, this is pi. There also you get minus 1. So minus and minus you got 2. If you cancel that above 2 from with this 4, then you got mu naught I by 2 pi a into n cap. Can you remember this? Note that here n cap represents the unit vector from the point O to P. Next one. Magnetic field produced along the axis of the current carrying circular coil. This is a current carrying circular coil. I think you all have a vision about this. If you see this, you can remember an equatorial axis, is it? Now, consider a current carrying circular loop of radius r. This radius is r and I be the current flowing through the wire, right? I be the current flowing through the wire. This is a circular loop, so I be the current flowing through the wire. The magnetic field at a point P, here the magnetic field is pointing at P on the axis of the circular coil. Okay, this is the axis of the circular coil at a distance Z. The distance between the O midpoint and the P is Z from its center of the coil O. Take two diametrically opposite line elements here, diametrically opposite line elements at C and D. Let R be the vector joining the current element IDL at C. Let R be the current vector joining the current element IDL at C. Therefore, PC is equal to PD. PC is equal to PD, which is equal to R, which is equal to R. Both PC and PD are equal to R. Therefore, R is equal to R square plus Z square. As the cosine law, R square plus Z square is equal to small r square. While taking square, you put a root in the opposite side, so R is equal to root of R square plus Z square, and angle CPO is equal to angle DPO. Angle CPO is equal to angle DPO, and altogether it is equal to theta. According to BIOTSAVART law, the magnetic field at P due to the current element IDL is dB mu naught, which is dB is equal to mu naught 4 pi IDL into R cap divided by R square. Here you can see the values. dB in the horizontal axis, and dB sin theta in horizontal axis, and dB Z in vertical axis. The magnetic field dB vector due to each current element IDL is resolved into two components, dB sin theta along y direction and dB cos theta along Z direction. Horizontal component of each current element cancel out, while the vertical component dB cos theta k cap along contribute to total magnetic field at the point P. Here you can see it's a 90 degree and this is also 90 degree, and dB is towards that, and this is the DL value. Current element pointing out of the page. Integrating around DL vector, the loop dB sweeps out a cone as shown in the figure. You can see a cone here. Now the net magnetic field at a point P is B is equal to integral dB vector, which is equal to dB cos theta into k cap. If you put the value of dB, that means mu naught I by 4 pi into integral dL by R square into cos theta into k cap. Then we know cos theta is equal to R by R square plus Z square, the whole root, or 1 by 2. If you substitute the value of R square in the cos theta in the equation, then we get, by Pythagoras theorem, R square is equal to small r square is equal to capital R square plus Z square, and integrating the line element from 0 to 2 pi r, we get B vector is equal to mu naught I by 2 pi into R square divided by R square plus Z square, the whole bracket 3 by 2. While substituting here, right, and the value for R square, we get a 2 here. That means the value for 2 pi r. If you cancel the 2 pi r and this 2 pi, then it is only this 4 pi, then you get only 2 pi. Then you can substitute all the values here, and because of this r square, it becomes a whole square. Here we have a root, so you put 3 by 2. Note that the magnetic field point along the direction from the point O to P. Current loop as a magnetic dipole. Magnetic field from the center of a circular loop of radius r along the axis is given by B vector is equal to mu naught I divided by 2 and r square divided by r square plus Z square, the whole 3 by 2 k. At a large distance, Z is very much greater than r. Therefore, r square plus Z square is equal to Z square. If it is a value, you can neglect the value of r square. Then we have, if you cancel the value, then r square is equal to 0. Then Z square, you can cancel this power and this 2. Then you get Z cube. That means B vector is equal to mu naught I r square divided by 2 into Z cube into k cap. Let A be the area of the circular loop. A is equal to pi r square. So rewriting the equation 1 in terms of area of the loop, we have B vector is equal to mu naught I by 2 R square divided by Z cube into K cap. If you multiply it and divide by 2, then we get B equal to mu naught I by 2 pi into A by Z cube into K cap. Compare the equation 2 with the equation 1 dimensionally, then we have Pm is equal to 1A, where Pm is called magnetic dipole moment in vector notation, then Pm is equal to IA. This implies that the current carrying circular loop behaves as a magnetic dipole of magnetic moment Pm. So the magnetic dipole of any current loop is equal to the product of the current and area of the loop. Next one, right hand thumb rule. In order to determine the direction of magnetic moment, we use right hand thumb rule. The mnemonic means to remember, which states that if we curl the fingers of right hand in the direction of current in the flow, then the stretched thumb gives the direction of the magnetic moment associated with the loop. Thank you, students. Remember, up to this we are going to have for the examinations. So study well up to this questions. That means up to session number 7.